Cross-bridge cycling forms the molecular basis for this sliding movement. Muscle contraction is initiated when muscle fibers are stimulated by a nerve impulse and calcium ions are released. The troponin units on the actin myofilaments are bound by calcium ions. The binding displaces tropomyosin along the myofilaments, which in turn exposes the myosin binding site.
Did you get that? Okay, do you see what was happening right there when the calcium bound to that? This moved from in front of these binding sites. They're actin binding sites, but they're binding sites for the myosin, okay? They're actin binding sites, but they say that this, I get concerned about the fact that they're saying these are myosin binding sites. Yeah, the myosin has to bind here, but these are considered the actin on the actin. It's a binding site for the myosin, okay? So it can be a little misleading here if you're unaware of what's really taking place here. Okay, let's go on.
At this stage, the head of each myosin unit is bound to an ADP and a phosphate molecule remaining from the previous muscular contraction. The myosin heads release these phosphates and bind to the actin myofilaments via the newly exposed myosin binding sites. The two myofilaments glide past one another, propelled by a head-first movement of the myosin units, powered by the chemical energy stored in their heads. As the units move, they release the ADP molecules bound to their heads. The gliding motion is halted when ATP molecules bind to the myosin heads, thus severing the bonds between myosin and actin.
Do you get that? The ATP has to bind on there, and then it can provide a release. And we can reset that head to go to another actin.
The ATP molecules are now decomposed into ADP and phosphate, with the energy released by this reaction stored in the myosin heads, ready to be used in the next cycle of movement. The myosin heads resume their starting positions along the actin myofilament and can now begin a new sequence of actin binding. The presence of further calcium ions will trigger a new cycle.
Does that make any sense? Locking and releasing. So, have you heard of rigor mortis? What is that? What's rigor mortis? A lot of you just acknowledge, yeah, I heard of rigor mortis. Well, what is it?
Isn't it when
No, it's not an isn't it. It is this.
It's when the body, when someone passes away, the body like the muscles get like hard,
The muscles do what?
like get hard, like
Hard. Okay. Anybody else want to weigh in? Go ahead.
It's a full lockup of the muscles. So if they usually have like a tightly like wound fist, and it's hard to like pull them apart. All the muscles in the whole body like do that exact kind of contraction.
When?
When
It happened, has it happened to you recently?
No.
Okay, so what is or when is or go ahead.
So it's what we just watched, the It Never Lets Go, the binding site. So it stays locked, and then it doesn't unlock.
When it happened to you today?
It happened when you pass.
after that.
I'm sorry?
After when the body passed,
Oh, when a person dies.
when the person died, it just stay there. It don't have the ATP, you don't have anything to unlock it. So it just kind of stay put, and now it just kind of
Locks up.
locks up forever because you
Rigor
mortis.
mortis, rigor, rigidity of death. Okay? So, why? Why do we get that lock up like that after death? And then the next question is, how long does it last? You all kind of led me, well, not all of you, but And so we, yeah, I know what rigor mortis is, yeah, I've heard that. Okay, so, not inaccurate what you've said, what you've reported here, okay, but why? Why does that happen?
Well, you're dead, so your body's not doing this anymore.
So you're dead, so your body's not what?
It's not
Generating?
functioning normal.
Not functioning normal, that would be true if you're dead, yes, that's true. Go ahead.
What we were talking about before is, since everything's shortened, ATP is needed to release the myosin head.
Uh-huh.
If you're not producing ATP anymore.
What's not producing ATP?
The myosin.
What's not producing ATP? Is you just, yeah, I'd like a field trip between here and New York. I don't wanna go from here to
Yeah.
New York. I want a field trip between here and New York, okay? And you just jumped me from Chicago to New York. That make sense? I guess it does. Did to me. You're gonna weigh into it? See? Tim's always up there giving me answers and stuff. Now he's just silent here. Right, what's not being produced?
ATP from mitochondria.
Why not?
Because there's no cellular respiration.
There's no aerobic cellular respiration taking place. So consequently, no ATP being produced. No ATP, how much ATP do you have stored up?
Seconds.
Seconds worth, right? Anthony, are you with me?
Yes,
So what happened? When the person died, what stopped?
mitochondria producing ATP.
Mitochondria activity with the production of, the aerobic cellular respiration, no ATP produced. So without the ATP, what stays put?
The head.
It locks. It doesn't release. The ATP is necessary to unlock the heads. Okay? So how quickly does that take place?
Quickly.
Really seems to depend on the ambient temperature. Ambient meaning what's the outside temperature of the body. That locking only takes place, but how long does rigor mortis last? Well, that's the thing of forensic medicine where you have a coroner who comes in and they say, well, the time of death was here, and how can you tell that? Well, we have some charts or graphs or things like that saying, generally speaking, under normal circumstances, weather temperatures like that, rigor mortis will take, it's going to be rigidity, full rigidity at this particular time, within this particular period of time. And then how long will that full rigidity last? What would stop that full rigidity from remaining that way? Have you heard of lysosomes?
Yeah.
What are, does anybody recall what lysosomes were?
Like that.
They're like, I don't know where that went, but they're like, what? Lysosomes. They're little garbage disposal packets within the cytoplasm of the cell. And what's their purpose? They're supposed to break down or degrade things. Well, as soon as you no longer have the integrity of the health of the body here, lysosomes say, hey, there's nothing keeping us contained. Exocytosis, just because they are little garbage disposal enzymatic activity, proteolytic enzymes, and they say, hey, we're not being contained any longer, let's go visit the cell. You and I start decaying from the inside and the outside shortly after death. If there's no life in this body, the decay is relatively quick, where there's the degradation or the deterioration of the body on the outside, but also from the inside. So how long does rigor last? Again, it can depend upon the ambient temperature here. But under most forensic evaluations, they say you've got a period of time. Rigor is going to be full rigidity. I mean, it starts slowly and then it fully, everything is locked up. There's a little bit of remaining ATP. Remember that? Be some left in the, yeah.
Why would that happen? Like, why would that tensing up happen? Like, what would kickstart that process?
What
If you weren't-
kickstarts which process?
The process of
The rigor,
Yes.
you just mentioned earlier, no ATP production, no release. The ATP is necessary for the release of the myosin heads. The myosin heads are all locked up.
But it still has to start though, right? The contraction still has to start, and if
Well, yeah, that whatever was the activity that was taking place at that particular period of time, and then there's gonna be a period of flaccidity. The body is, just working with what is still available as ATP in action of those muscles, and there's the fluidity of the motion. There's the flaccidity, and then it starts to lock up. Then the rigor starts to set in, and there's a period of time. Usually they consider hours, not necessarily, it's not within minutes or something like that, but once again, ambient temperature can play a role in that. And then there's this period of time of increased rigidity, full rigidity, and then we start to have the proteolytic enzymes kick in to start to decay. Okay, and then at that point, go ahead, what?
So after the full rigidity, would that be considered like denaturing of the proteins? And that's why
After a period of time, it would be what?
denaturing of the proteins? Is
Yes,
that-
yes, because the proteolytic enzymes are starting you're starting the decay process, the breaking down of the contractile proteins within the system there. Yes, that would be accurate. And so we're gonna have the breakdown of this take place. And then we have, go into full decay here on the body, okay? You hear about, you don't have to, any dead animal on the road or something like that. When you go down the road and you see the raccoon and he's up there like this, in full rigidity, right? And then, there's the flaccidity. So rigor mortis is a real deal based on the fact that we need to have the ATP there in order to allow for normal contraction, release of the myosin head. And then when we no longer have that, then we have the proteolytic enzyme breakdown. I'll take 10 minutes here. Come on back in here. You can't depend on that.